Welcome to the Deep Sleep Science Channel. Tonight, we're drifting gently beneath the night sky, a place where a single glance can carry you from the thin edge of Earth's atmosphere to galaxies millions of light years away. As you settle in, you'll slowly uncover how every quiet point of light above you is part of something much larger, moving, changing, and connected in ways most people never notice. So before you begin to relax completely, take a moment to like, subscribe, or leave a commenter, and then let your mind wander softly upward as we explore the calm, hidden depth of the night sky together. The night sky is a record of time, because the farther away something is, the longer its light has taken to reach us. When you look up, you are not seeing everything as it is right now. You are seeing a layered history of light arriving from many different distances, all at once. Even the nearest star beyond our sun is seen as it was years ago, not as it is in this exact moment. Light needs time to travel, even across the relatively nearby parts of the universe. So every starry view is also a glimpse into the past. The Andromeda galaxy can be visible to the naked eye from a dark place, even though its light began its journey long before humans built cities. That means a faint blur in the sky can carry light that has crossed space for about 2.5 million years. It is a quiet reminder of just how deep the universe really is. A single dark sky can include nearby satellites, objects in our solar system, stars within our galaxy, and even other galaxies all in one view. Some things overhead are only a few hundred kilometers away, while others are unimaginably distant. The night sky looks flat to the eye, but it is actually filled with layers stretching across vast depths. The night sky is not fixed scenery at all, but a layered view made of atmosphere, solar system dust, stars, glowing gas, dark clouds, and distant galaxies. What appears simple at first is actually a rich stack of different kinds of matter and light. Looking up is less like seeing a ceiling and more like peering into a deep, structured universe. The Milky Way appears as a pale band across the sky because we are looking through the flat disk of our own galaxy from inside it. Instead of seeing our galaxy from the outside, we are embedded within it, so our view runs through crowded regions full of stars. That is why the sky can sometimes show a soft, glowing river of light. When you look at the Milky Way, you are seeing countless unresolved stars blended together. Most of those stars are too faint or too crowded to separate with the naked eye, so they merge into a misty glow. What seems like a cloud is often an enormous concentration of starlight. The brightest part of the Milky Way marks the direction toward the crowded central regions of our galaxy. In that direction, the stars, dust, and gas become much denser. So when that part of the Milky Way arches overhead, you are looking toward one of the busiest regions in the galaxy we call home. Dark lanes crossing the Milky Way are not empty gaps, but huge clouds of dust blocking the starlight behind them. They look like missing patches, yet they are actually signs that something is there. In a gentle way, even the darkness in the sky can reveal structure. Our galaxy is not just a simple flat sheet of stars. It has a disk, a central bulge, and a surrounding halo, each with different kinds of stars and motions. So the night sky is showing us only a thin visual slice of a much more complex galactic structure. The Milky Way is so broad across the sky because its real structure spans enormous distances through space. We are not seeing a small local feature, but part of a galaxy that stretches across a huge cosmic scale. Its width in the sky reflects the immense size of the system we live inside. Some apparently dark and enter-looking regions of the Milky Way are actually dust clouds hiding richer star fields behind them. A telescope or infrared survey can reveal that what looked blank is sometimes full of stars concealed by cosmic dust. So even empty patches can be full of hidden detail. On a truly dark night, the sky can show structure from horizon to horizon instead of only scattered points of light. Under those conditions, the sky begins to feel textured, layered, and full. It becomes easier to sense that the heavens are not just dotted with stars, but shaped by larger patterns. The darkest skies reveal not only more stars, but also stronger contrast between bright and faint parts of the Milky Way. In a bright city, much of this subtle structure is washed away. In a dark place, the galaxy's uneven brightness becomes much more noticeable and much more real. Many of the night sky's most impressive sights, including the Milky Way, zodiacal light, and bright meteor showers, do not require a telescope at all. They are large, open sky phenomena, best seen simply by looking up under dark conditions. Sometimes the grandest things in astronomy are the ones meant to be viewed with the unaided eye. Auroras can make the sky look alive, with curtains, arcs, and rays that shift over the course of minutes. These moving lights are not distant stars or reflections from clouds, but activity in Earth's own upper atmosphere. It is one of the most dramatic ways the night sky can visibly change while you watch. During a total solar eclipse, stars and bright planets can appear in the daytime because the sun's bright face is blocked. For a brief moment, the sky behaves more like twilight than noon. It is one of the rare times when day and night seem to overlap. The sun's corona is usually hidden by glare, but during totality in a solar eclipse, it becomes visible as a delicate outer halo. This faint outer atmosphere of the sun normally disappears in the overwhelming brightness of daylight. Only when the sun's main disk is covered does that hidden structure emerge to view. A lunar eclipse can turn the moon red or orange because sunlight reaching it has passed through Earth's atmosphere. Blue light is scattered away more strongly, while redder light bends through and continues onward to the lunar surface. In that sense, the eclipsed moon is lit by filtered sunlight passing through the rim of Earth's skies. The exact stars you can see at night depend strongly on your latitude, because different parts of the celestial sphere rise above the horizon in different places on Earth. Someone far north and someone far south do not look into the same sky in quite the same way. Your position on Earth quietly shapes the map overhead. The season changes the night sky as well, because Earth moves around the sun during the year. As a result, the nighttime side of Earth points toward different regions of space in different months. That is why familiar constellations slowly trade places through the seasons. The night sky changes over the course of a single night because Earth rotates once about every 24 hours. This steady turning makes stars appear to rise in the east and sink in the west. The sky seems to move, but the motion we feel is really our own world turning beneath it. Stars near the celestial poles can be circumpolar, which means they never drop below the horizon for observers at certain latitudes. Instead of rising and setting, they circle around the pole night after night. For some people, a portion of the sky is always present. Astronomers divide the sky into 88 official constellations, and every point overhead belongs to one of them. In modern astronomy, this creates a complete map of the heavens. It means the whole sky has been organized into named regions, much like countries on a globe. A constellation in modern astronomy is more than a familiar pattern of stars. It is an officially defined region with boundaries, so any object in the sky can be said to lie within one constellation or another. This makes constellations useful not only for storytelling, but also for precise sky mapping. Many famous star patterns, such as the Big Dipper, are asterisms rather than full constellations. An asterism is simply a recognized pattern, not an official sky region. So some of the shapes people know best are actually parts of larger constellations. The stars in a constellation usually only appear close together from our point of view on Earth. In space, they may be separated by very large distances and have no close relationship at all. What looks like a neat pattern is often a visual arrangement created by perspective. The celestial equator is an imaginary projection of Earth's equator onto the sky. Objects near it can be seen from a large portion of the world because it lies between the far northern and far southern sky. It helps connect the geography of Earth with the geometry of the heavens. Right ascension and declination serve as sky coordinates, much like longitude and latitude do on Earth. They allow astronomers to locate objects overhead with precision. Even the seemingly open and fluid night sky can be mapped with an orderly grid. The zenith is the point directly overhead, and every observer has a different zenith depending on where they are standing. It is one of the most personal points in the sky because it belongs to your own location. Move across Earth, and your zenith moves with you. The meridian is an imaginary north to south line passing overhead through the sky. When an object crosses it, that object reaches its highest point above the horizon for that night. This makes the meridian especially useful for observations because objects are often clearest when they are highest. Twilight is not truly over until the sun is 18 degrees below the horizon. That is why the sky remains bright for a while after sunset, even when the sun itself is gone from view. Earth's atmosphere continues scattering sunlight long after the sun has dipped below the edge of the world. Astronomical twilight is the stage after sunset when the sky finally becomes dark enough for most faint stars to appear. Before that point, lingering sunlight in the atmosphere still softens the darkness. Only once the sun is far enough below the horizon does the deeper sky fully emerge. Planets stay near the ecliptic because their orbits lie in roughly the same flat plane around the sun. This is why the bright wandering planets tend to travel through a familiar band of sky rather than appearing anywhere at random. Their shared orbital history leaves a visible pattern in the heavens. The ecliptic is the apparent yearly path of the sun across the background stars. Of course, what is really happening is Earth moving around the sun. But from our viewpoint, the sun seems to drift slowly through the constellations. This path becomes one of the main organizing lines of the sky. The zodiac is the band of constellations along the ecliptic through which the sun, moon, and planets appear to move. It is not a random collection, but a sky zone shaped by the flat arrangement of the solar system. When you notice planets shifting from one season to the next, they are usually traveling within this band. Inferior planets such as Mercury and Venus always appear fairly close to the sun in the sky because their orbits lie inside Earth's orbit. From our perspective, they never wander far away from the sun's direction. That is why they are usually seen in evening or morning twilight rather than high at midnight. Superior planets such as Mars, Jupiter, and Saturn can appear much farther from the sun in the sky and may remain visible for much of the night. Because their orbits lie beyond Earth's, the viewing geometry allows them to spread wider across the ecliptic. This gives them a much larger stage in the night sky. A conjunction happens when two sky objects appear close together from Earth, even if they are actually very far apart in space. It is a matter of line of sight rather than true physical closeness. The sky often creates these elegant pairings through perspective alone. Opposition is the position in which a planet lies opposite the sun in the sky, making it visible from sunset until sunrise. At that time, the planet rises as the sun sets and stays in view all night long. For outer planets, opposition is often one of the best times to observe them. Planets usually shine with steadier light than stars because they appear as tiny disks rather than perfect points. Atmospheric turbulence bends their light too, but the effect is averaged across that slightly wider image. So stars tend to twinkle more sharply, while planets often glow in a calmer way. The apparent backward drift of some planets against the background stars is called retrograde motion. This does not mean the planet has truly reversed its orbit. It happens because Earth and the other planet are both moving, and the shifting viewpoint changes how the planet seems to slide across the sky. The apparent fixedness of the stars is only relative. Stars are moving through space, but they are so far away that their changes are very slow from a human point of view. Over a single lifetime, most of those motions are too small to notice with the naked eye. Over long periods, stars do shift their positions due to proper motion. Their patterns are not eternal, even if they seem stable over centuries of ordinary observation. Given enough time, the familiar constellations would gradually reshape themselves. Precession slowly changes the direction of Earth's axis over thousands of years. Because of that slow wobble, the identity of the pole star changes over long stretches of time. The sky's framework is stable on human timescales, but not forever. Polaris is important because Earth's north rotational axis points close to it, making it appear nearly fixed in the northern sky. While other stars seem to circle around it, Polaris stays almost in place. That steadiness made it especially useful for orientation and navigation. Polaris is not the brightest star in the sky, even though it is one of the most famous. Its importance comes from its position, not from its brilliance. In astronomy, usefulness and brightness are not always the same thing. Because of the difference between solar time and sidereal time, stars rise about 4 minutes earlier each night. That small change adds up steadily over weeks and months. It is one of the main reasons the evening sky slowly shifts through the year. This nightly 4-minute shift is why winter constellations are gone from evening skies by spring. The stars have not disappeared, but the timing of Earth's rotation and orbit has changed when they are visible after dark. Seasonal sky change is really a slow clockwork effect. The same star field that is overhead at midnight in one season may be overhead in the early evening a few months later. As Earth moves around the Sun, nighttime faces those same regions of space at different hours. So the sky keeps its patterns, but changes their timing. The quiet appearance of the night sky hides constant motion, including Earth's rotation, Earth's orbit, the Moon's motion, and the movement of planets. Even when the sky feels still, everything in the scene is in motion. Calmness in the night sky often comes from slowness, not from stillness. Because the sky repeats its broad seasonal patterns each year, it can feel familiar while still changing from night to night. Certain constellations return to the same seasons, yet the moon, planets, and atmosphere always add small differences. The sky is both dependable and never exactly the same twice. No two clear nights are completely identical because moon phase, atmospheric conditions, season, and the motions of planets and satellites all keep changing the view. Even if you stand in the same place, the sky above you is always a little different. Night after night, the universe offers variation in quiet ways. Sirius is the brightest star in the night sky, as seen from Earth. It stands out so clearly that even people who know very little about astronomy often notice it right away when it is in season. Its brightness gives it a special presence in the sky, making it one of the easiest stars to recognize. Sirius appears so bright partly because it is both truly luminous and relatively close to Earth. Some stars are bright because they produce enormous amounts of energy, while others seem bright because they are nearby, and Sirius benefits from both of those advantages. That combination helps it shine with unusual strength in our sky. Canopus is one of the brightest stars in the sky, but many people in northern locations never see it because it lies too far south. This means visibility is not only about brightness, but also about where a star sits on the celestial sphere. A star can be extremely prominent in one part of the world and completely absent in another. Arcturus is a bright orange giant and one of the most noticeable stars in the northern sky. Its warm color makes it stand apart from many whiter or bluer stars nearby. When people describe stars as looking golden or amber, Arcturus is one of the clearest examples. Vega is one of the bright stars of northern summer and forms part of the summer triangle. Because it is both bright and well placed in warm season skies, it becomes a familiar marker for many sky watchers. It often serves as one of the easiest entry points for learning summer star patterns. Betelgeuse is a variable red supergiant, which means its brightness changes over time. It is not always shining at exactly the same level, because the star itself goes through physical changes that affect how much light we receive. This makes it a reminder that stars are not all constant points, but active bodies that can shift in visible ways. Aldebaran is an orange giant that appears in front of the Hyades cluster, but it is not actually a true member of that group. It only seems to belong with those stars because of the way our line of sight works from Earth. In space, it is arranged differently from the cluster behind it, even though the sky makes them look connected. Antares is a red supergiant whose deep color makes it easy to notice in Scorpius. That reddish tone gives the star a strong personality in the sky and helps explain why it has attracted attention for so long. Its appearance is a visible clue to the nature of the star itself. Procyon is one of the bright stars of winter in the northern hemisphere. It often appears as part of the larger winter sky scene that includes other major bright stars. Because it is easy to see and placed among well-known seasonal stars, it helps shape the look of winter nights. Pollux is the brighter of the two main stars associated with Gemini. Although the pair is often spoken of together, they are not equal in brightness when you look carefully. Pollux quietly dominates the pair and gives Gemini one of its most recognizable features. Castor looks like a single bright star to the eye, but it is actually part of a multiple star system. What seems simple from a distance can turn out to be more complicated when studied more closely. This is one of many ways the sky teaches that appearances can hide deeper structure. Alpha Centauri is one of the nearest star systems to Earth, but most observers in northern regions cannot see it because it lies far south. Its nearness makes it especially important in astronomy, yet geography still limits who gets to enjoy it directly. Even nearby stars are not equally available to all people on Earth. Many bright stars appear blue-white, yellow, orange, or red because stars have different surface temperatures. Their colors are not random decoration, but real signs of physical conditions. In a quiet way, the color of a star acts like a clue about how hot its outer layers are. Blue-white stars are generally hotter at the surface than orange or red stars. So when a star looks bluish, that color often points to a more intense surface temperature. The night sky, then, is not only beautiful to look at, but also full of visible physical information. Some stars visibly change brightness because they expand, contract, eclipse one another, or erupt. There are several different reasons a star may vary, and not all variable stars behave in the same way. This means that changes in brightness can reveal many kinds of activity happening across space. A binary star is a pair of stars bound together by gravity, and many stars belong to such systems. In fact, single stars like our Sun are not the only common arrangement in the universe. Many of the lights overhead are part of gravitational partnerships, even if they look solitary to the eye. The apparent brightness of a star does not tell you its true power unless you also know its distance. A faint-looking star might actually be tremendously powerful but very far away, while a brighter-looking one may simply be much closer. To understand stars properly, brightness has to be paired with distance. The magnitude scale works backward, so smaller or more negative numbers mean brighter objects. This can feel a little strange at first because it runs opposite to everyday expectations. But once understood, it becomes a useful way to compare how bright different objects appear in the sky. The name Milky Way comes from the galaxy's faint milky appearance across dark skies. Long before modern astronomy explained what it really was, people noticed that it looked like a pale glowing band. The name preserves that old visual impression in a simple and very human way. The band of the Milky Way is much easier to see from dark locations because artificial light washes out its low contrast. It is not only a matter of brightness, but of delicate contrast between the galactic glow and the background sky. Even a rich galaxy can vanish from view when the sky around it is made too bright. Infrared surveys reveal parts of the Milky Way that visible light cannot show clearly because dust blocks visible wavelengths. In ordinary sight, dust hides large sections of the galaxy, especially in crowded regions. But in infrared light, astronomers can peer through much of that dust and uncover structures that would otherwise stay hidden. The Milky Way's appearance changes with season and latitude because different sections are overhead at different times and in different parts of the world. The galaxy itself is not rearranging, but our viewpoint keeps shifting as Earth rotates and orbits the Sun. That is why the galactic band can feel so different from one place or season to another. The Andromeda galaxy can be seen with the naked eye from a dark site as a faint, elongated smudge. It does not look like the sharp, detailed galaxies seen in photographs, but as a soft patch of light. Even so, the fact that human vision can detect another galaxy at all is extraordinary. The Large Magellanic Cloud is a nearby galaxy visible mainly from the southern hemisphere. For southern observers, it is one of the most striking galactic companions in the sky. For many northerners, however, it remains an unseen wonder, simply because of earthly position. The Small Magellanic Cloud is another nearby galaxy that appears as a detached cloud-like patch in southern skies. It looks modest to the eye, but it represents an entire galaxy beyond our own. A small, faint patch can therefore stand for an enormous system of stars. The Pleiades star cluster is easily visible to the unaided eye and is one of the most recognizable star groups in the sky. Its compact, sparkling appearance makes it memorable even for beginners. Because the group is both pretty and easy to spot, it has been noticed and named by many cultures. The Hyades form a broad V-shaped pattern in Taurus, but Aldebaran only appears in front of them by chance alignment. This gives the impression that the bright star belongs naturally inside the pattern, even though it is arranged differently in space. It is another example of how sky patterns are shaped by perspective. The Beehive cluster can sometimes be seen without optical aid from a dark location as a soft patch in Cancer. Under less favorable skies, it may go unnoticed, but darkness allows its gentle glow to stand out. It shows that some clusters can be felt first as a haze before being resolved into stars. Globular clusters differ from open clusters because they are denser, older, and far more spherical. Open clusters are usually looser and younger, while globular clusters are tightly packed systems containing many ancient stars. These two cluster types tell very different stories about how stars are grouped in the universe. Nebulas can be emission, reflection, or dark nebulas depending on whether they glow, reflect light, or block light. In other words, a nebula may shine by its own energized gas, glow by borrowed starlight, or appear mainly as darkness against something brighter. The sky's clouds of gas and dust come in several distinct visual forms. The Orion Nebula is one of the few nebulas visible to the naked eye and appears as a fuzzy patch in Orion's sword. Even without a telescope, you can detect that it is not quite star-like. It is one of the simplest ways for the eye to sense a true cloud of star-forming material in space. The Orion constellation is visible from much of the world because it lies near the celestial equator. That placement makes it accessible to observers in both northern and southern regions. It is one of the reasons Orion has become one of the most widely recognized constellations on Earth. Orion's belt is an asterism made of 3 bright stars lined up closely in the sky. The neatness of that line makes it unusually easy to identify, even for someone new to stargazing. It acts like a signpost, helping people find the rest of Orion and nearby sky features. The Big Dipper is part of Ursa Major and is commonly used to find Polaris by extending the line through the 2 outer stars of its bowl. This makes it more than just a famous pattern. It also becomes a practical tool. A simple shape in the sky can guide the eye toward true north. Cassiopeia's W-shaped pattern is a useful northern sky marker opposite the Big Dipper around Polaris. Because of that position, it can help skywatchers when the Dipper is low or awkwardly placed. Together, these 2 patterns make northern sky orientation much easier. Scorpius is especially striking because its curved pattern resembles the tail of a scorpion. The constellation has a shape that feels more creature-like than many others, which helps it stand out in memory. It is one of the clearest cases where the traditional name matches the visual impression. Sagittarius points toward the dense star fields of the Milky Way's central direction. When you look that way, you are facing one of the richest and most crowded parts of our galaxy. So this constellation is not only a pattern, but also a guide toward deep galactic structure. The Southern Cross is a compact constellation used by southern observers as a directional guide. Though smaller than many people expect, it has long been important for navigation and orientation. Its usefulness comes from both its shape and its placement in the southern sky. The 2 bright pointer stars near the Southern Cross help distinguish it from similar-looking patterns nearby. Without them, it can sometimes be easier to confuse the cross with other star arrangements. These extra stars act like companions that confirm you are looking at the right guide. The Summer Triangle is not a constellation, but an asterism formed by Vega, Deneb, and Altair. Even though it is unofficial in the strict astronomical sense, it is extremely useful for learning the summer sky. Its large, clear shape makes it one of the easiest seasonal patterns to recognize. Deneb, one of the stars of the Summer Triangle, is extremely luminous even though it is very far away. The fact that it still appears bright to us means the star must be producing an enormous amount of light. Distance and brightness together reveal just how powerful it really is. Some star names still preserve Arabic, Latin, and Greek roots, reflecting a long multicultural history of sky observation. The language of the night sky carries traces of many civilizations that watched, named, and studied it. In that way, astronomy is also a record of human memory. Traditional constellations were named after animals, mythic figures, and objects long before modern astronomy standardized the sky. These old names remind us that people first met the stars through story, imagination, and daily life. Scientific mapping came later, building on much older habits of skywatching. Different cultures grouped stars into very different patterns, even when looking at the same sky. The stars themselves were the same, but human interpretation varied widely. This shows that sky patterns are partly physical and partly cultural. The modern official constellation system does not erase older sky traditions. It mainly provides a shared scientific map. Astronomers need a common framework for locating objects precisely, but that practical system exists alongside many older ways of understanding the sky. Scientific order and cultural meaning can both remain present. Ancient navigators used the steady motions of stars to guesstimate direction and season. Long before modern instruments, the sky acted as a dependable guide for travel and timing. The regular behavior of the heavens made it one of humanity's earliest practical tools. Polaris is useful for navigation in the northern hemisphere because its height above the horizon roughly matches your latitude. That means its position can tell you not only direction, but also something about where you are on Earth. A single star can therefore serve as both compass and rough measuring tool. In the southern hemisphere, navigators often use the Southern Cross and nearby stars to locate the South Celestial Pole. Because there is no bright southern equivalent to Polaris, the method is a little different. Instead of one obvious pole star, southern navigation relies more on star patterns. The heliacal rising of certain stars was historically important for calendars and agriculture in many cultures. When a star first became visible again before dawn after a period of absence, people treated that appearance as a seasonal marker. The sky therefore helped organize planting, harvest, and ritual time. The night sky served as one of humanity's earliest long-term records of recurring natural patterns. Before clocks, printed calendars, or modern data systems, the heavens offered a reliable sequence of changes that repeated year after year. Watching the sky was one of the earliest ways humans learned to track time on a large scale. Many meteor showers retain names based on constellations that were formalized much later than the phenomena themselves were noticed. This means the naming system mixes older sky events with later organized star maps. Even in modern astronomy, present-day labels often sit on top of much older experiences of the sky. Meteor showers happen when Earth passes through streams of debris left behind by comets and, in some cases, asteroids. These streams are made of countless small particles spread out along an orbit. When Earth moves through one of those dusty paths, many particles enter the atmosphere over a short period of time. And that is why the sky can suddenly produce repeated streaks of light on particular nights each year. A meteor is the streak of light produced when a small particle rushes into Earth's atmosphere and heats the surrounding air. The glowing line is not the object itself simply burning like a piece of wood in a fire. Instead, it is a fast, energetic interaction between the particle, the atmosphere, and the hot gases created during entry. If part of that incoming object survives its trip through the atmosphere and reaches the ground, it is called a meteorite. So the bright flash in the sky is a meteor, while the piece that lands is a meteorite. This distinction matters because many people use the words as if they mean the same thing, but in astronomy they describe different stages of the same event. Meteor showers are named after the constellation, or star region, from which the meteors appear to radiate. This point is called the radiant, and it is a perspective effect rather than a true physical source in the sky. The particles are arriving along parallel paths, but to our eyes they seem to spread outward from one area, much like distant roads appearing to meet at a single point. The Perseids are especially well known because they are both rich and dependable, and they occur during warm northern nights when many people are comfortable outside. Their combination of good timing and strong activity has made them one of the most popular annual sky events. They are a fine example of how astronomy can sometimes be both predictable and widely accessible. The Geminids are unusual because they come from the rocky body 3,200 Phaethon, rather than from a more typical icy comet. Most major showers are linked to comet debris, so the Geminids stand apart in origin. That makes them especially interesting because they show that not all meteor streams come from the same kind of parent object. The Orionids and Eta Aquariids are both connected to Comet Halley. This means the same famous comet has left material in its orbit that Earth meets at different points of the year. One comet, moving along its long path around the Sun, can therefore give rise to more than one recurring meteor shower. Leonid storms can become spectacular in some years because their parent comet leaves behind dense dust trails. In ordinary years, the shower may be modest, but when Earth passes through a richer stream, the number of meteors can rise dramatically. This shows how the structure of a debris trail can strongly change what observers experience below. Most meteor shower particles are tiny, often no larger than grains of sand or peas. Even such small pieces can create striking streaks of light because they move so quickly and release energy as they hit the atmosphere. A meteor can look dramatic, even when the original particle was very small. Meteors can leave persistent glowing wakes when the upper atmosphere remains ionized after the particle has passed through. The light may linger briefly as a soft, twisting trace. This means the meteor's visible effect can outlast the object's main flash, leaving behind a temporary mark in the sky. Sporadic meteors can appear on any clear night, even when no major shower is active. These are not part of one well-known annual display, but simply isolated bits of material entering the atmosphere at random times. So even an ordinary quiet night can still offer an unexpected streak of light. A fireball is an exceptionally bright meteor. It outshines ordinary meteors and can be dramatic enough to catch the attention of people who were not even looking upward. The category is based on brightness, showing that some incoming particles produce much stronger visible effects than most. Bolides are meteors that explode or fragment dramatically in the atmosphere. Instead of remaining a simple streak, they may flare, break apart, or produce a sudden burst of light. These are among the most energetic and visually intense meteor events seen from the ground. The radiant of a meteor shower is a perspective effect, much like railroad tracks seeming to meet in the distance. The particles are not actually starting from one point in space over the constellation. They only seem to spread outward from that point because of the way parallel motion looks from our viewing angle. Meteors become visible when fast entry causes heating, compression, and glowing in the surrounding air and material. The process is not just the object rubbing against the air in a simple, everyday sense. It is a high-speed atmospheric interaction that creates light through intense physical changes in both the particle and the gases around it. Meteor showers are usually best after midnight, because at that time your side of Earth is turning into the incoming stream of particles. Earlier in the evening, you are standing more on the trailing side of the planet. After midnight, your location faces more directly into the path of the debris, which increases the number of meteors you can see. Moonlight can greatly reduce the number of meteors visible to the eye, because it brightens the background sky. Fainter streaks that would be easy to notice under dark conditions can disappear into that added glow. So a meteor shower's true activity may be much greater than what a bright moon allows you to detect. Dark skies matter more for meteor watching than magnification, which is why showers are usually best viewed with the naked eye. Meteors can appear anywhere across a wide area of sky, so optical instruments often limit rather than help the view. A broad, dark, unobstructed sky is usually the best tool. The fastest meteors usually come from streams whose particles meet Earth head-on at very high relative speed. That stronger collision with the atmosphere creates a swift, sharp, energetic streak. Their motion can feel almost instant because the relative speed is so great. Slow meteors often seem to last longer because they move more gently across the sky. Their motion gives the eye slightly more time to follow them. This difference in appearance reminds us that meteor speed changes from one shower or one particle to another. Auroras are caused when energetic particles from the Sun interact with Earth's magnetic field and atmosphere. These particles do not simply strike the sky directly in a straight line everywhere. Earth's magnetic environment guides and concentrates them, turning solar activity into glowing patterns high above the planet. Auroras are most common near the Arctic and Antarctic circles because charged particles are guided toward the polar atmosphere. Earth's magnetic field funnels much of this activity toward high latitudes. That is why the far north and far south are the natural homes of the most frequent auroral displays. Green auroral light often comes from oxygen high in the atmosphere. The exact color depends on the type of atom or molecule involved and the energy conditions of the interaction. So the green seen in many auroras is a real physical signature of atmospheric oxygen responding to incoming energy. Red auroras can also be produced by oxygen, but generally at higher altitudes and under different conditions than green ones. This means the same element can create different visible effects depending on where the interaction happens and how energetic it is. Color in an aurora is therefore a clue to the physics taking place above. Nitrogen contributes blue and purplish auroral colors. When nitrogen molecules are excited in the upper atmosphere, they can add cooler toned shades to the display. This gives auroras some of their richer variety and helps explain why they can shift from one color family to another. Large geomagnetic storms can push auroras much farther from the poles than usual. Under strong solar disturbances, the zone of visible activity expands, allowing people at lower latitudes to witness displays that are normally too far away. This makes major auroral events especially memorable. Earth's magnetosphere is stretched away from the sun by the solar wind, helping create the long magnetotail involved in auroral activity. This shows that auroras are not only about Earth's atmosphere, but also about Earth's larger magnetic relationship with the sun. The visible lights are tied to a much bigger invisible structure in space. Auroras can occur during shorter, more localized geomagnetic substorms, as well as during larger geomagnetic storms. Not every auroral display requires the most extreme solar conditions. Some are produced by smaller bursts of magnetic activity that still rearrange charged particles in important ways. Auroras are atmospheric light displays, not reflections from ice or clouds. Even though they can look soft, flowing and curtain-like, they are created high in the atmosphere by energized particles and glowing gases. Their beauty comes from real physical processes rather than from simple reflection. Airglow is a natural faint glow of the night atmosphere caused by chemical processes high above Earth. Even on nights without auroras, the atmosphere itself is not entirely dark. It can produce a subtle background light that becomes more noticeable in photographs or very dark observing conditions. Airglow can make even very dark skies look slightly greenish, reddish, or banded in photographs. Cameras collecting light over time can reveal these gentle atmospheric colors much more clearly than the human eye usually can. So a photograph may show that the sky itself was quietly glowing all along. Airglow is not the same as aurora, because it occurs more generally and does not require strong geomagnetic activity. Auroras are tied to solar particles and magnetic disturbances, while airglow is part of the normal behavior of the upper atmosphere. Both create light, but they come from different causes. Airglow contributes to the natural brightness floor of the night sky. This means that even in the absence of city lights, moonlight, and strong auroras, the sky is still not perfectly black. Nature itself provides a faint baseline glow. Zodiacal light is sunlight scattered by dust particles orbiting the sun in the inner solar system. These dust grains are spread through the plane of the solar system, and when sunlight hits them at the right angle, a faint glow becomes visible from Earth. So part of the night sky's softness comes from dust floating between the planets. Zodiacal light usually appears as a faint triangular or conical glow extending from the horizon along the ecliptid. It is not a cloud in Earth's atmosphere, but a solar system phenomenon aligned with the same general plane in which the planets move. Its shape reflects that geometric arrangement. Zodiacal light is easiest to see when the ecliptic stands steeply above the horizon after dusk or before dawn. In that position, the glow rises more clearly away from horizon haze and scattered light. The same phenomenon can therefore be much easier or harder to spot, depending on season and latitude. The Gegenschein is a very faint brightening of the sky opposite the sun, also caused by interplanetary dust. It is subtler than zodiacal light and much less obvious to ordinary observers. Even so, it is another sign that sunlight interacts gently with the dust spread through our solar system. The Gegenschein is usually much harder to notice than zodiacal light and generally requires very dark skies. Its faintness means it is easily lost to moonlight, haze, or artificial lighting. Detecting it is often more about sky quality than about eyesight alone. Noctilucent clouds are high enough to remain sunlit after sunset, which is why they can shine while the ground below is already dark. Their height places them in a region where the sun can still reach them long after lower clouds have entered shadow. That is what gives them their unusual glowing appearance. Noctilucent clouds form in the mesosphere, roughly 76 to 85 kilometers above Earth. This makes them far higher than ordinary weather clouds. Their location alone explains why they behave so differently from the familiar clouds of the lower atmosphere. These clouds can fall around tiny bits of meteoric dust high in the atmosphere. Small particles act as surfaces on which ice can gather under the right conditions. In this way, material from space can help shape a delicate phenomenon visible from the ground. Noctilucent clouds are sometimes called night-shining clouds. The name is simple and descriptive because they can remain bright after sunset in a way that feels unusual and striking. The term captures the visual experience without changing the science behind it. They are seen most often at high latitudes during summer. This seasonal and geographic pattern comes from the special temperature and lighting conditions needed for them to form and remain visible. So their appearance depends on a precise balance of place and season. Their great height lets noctilucent clouds catch sunlight after lower clouds are already in darkness. That single fact explains much of their unusual beauty. They are still lit from above, while the rest of the sky below has already entered night. Transparency describes how clear the atmosphere is, and it strongly affects how many faint stars you can see. A transparent sky allows more light from celestial objects to pass through without being scattered or absorbed. So good transparency is essential when trying to detect delicate, dim features in the night sky. Seeing describes how steady the atmosphere is, and it affects how sharp stars and planets look through telescopes. Even a clear sky can blur fine detail if the air is turbulent. This is why a beautiful-looking sky to the naked eye is not always ideal for telescopic observing. A crystal-clear night can still have poor seeing if the air is unstable and turbulent. In that case, faint objects may be visible, yet bright stars and planets can appear to shimmer and blur when magnified. Clarity and steadiness are related to different atmospheric qualities. A hazy night can sometimes have very steady seeing, even while faint objects are harder to spot. The sky may not be transparent enough for deep, faint views, but the calmness of the air can still allow sharp planetary detail. This shows that different types of observing depend on different atmospheric strengths. Humidity, dust, smoke, and haze all reduce contrast in the night sky by scattering light. They brighten the background and soften the visibility of faint objects. Much of successful sky watching then depends not only on what is above us in space, but on what is floating in the air around us here on Earth. Light pollution is artificial sky glow that makes the background of the night brighter and hides faint stars. Instead of the sky acting like a dark canvas, extra human-made light fills it with a washed-out brightness. This means many delicate objects are still overhead, but they become much harder or even impossible to see. Light pollution does not only affect city centers, because its glow can spread far beyond the place where the lights are installed. Light scatters through the atmosphere, and creates a dome of brightness that reaches into surrounding areas. That is why even places that seem rural can lose much of their natural darkness if a city is nearby. The Milky Way is one of the first major sky features to disappear as light pollution increases. Its glow is broad and gentle rather than sharp and intense, so it is easily overwhelmed by a bright background sky. In many populated areas, people lose sight of their own galaxy long before they realize how much is missing. Shielded lighting helps protect dark skies because it reduces wasted light shining upward or sideways. When light is directed only where it is actually needed, less of it spills into the atmosphere. A simple change in how lights are designed can therefore make a meaningful difference for the sky. Blue-rich, artificial light tends to scatter strongly in the atmosphere and can worsen sky glow. Shorter wavelengths spread more easily through the air, so lighting that contains a lot of blue can brighten the sky more effectively than warmer-colored light. This means the type of lighting matters, not only the amount. Dark sky scales such as the Bortle scale are used to describe how bright or dark a sky appears to an observer. These systems help people compare viewing conditions from one place to another in a more organized way. A sky is not just called dark or bright in general terms, but can be described with a clearer standard. A naturally dark sky contains much more than stars alone, including airglow, zodiacal light, and diffuse starlight. Real darkness is not the same as emptiness. Even when artificial light is absent, the sky still carries a soft, natural richness made of many subtle kinds of light. Satellite constellations can affect the appearance and study of the night sky by adding moving light trails. These objects do not stay fixed like stars, and they can cross a telescope's field or a long exposure image at inconvenient moments. So modern human technology has begun to change not only life on Earth, but the visual character of the sky itself. Radio interference can also affect astronomy, which is why dark and quiet skies are both important. Some observatories do not only need freedom from visible light pollution, but also from human-made radio signals. The night sky is studied in many wavelengths, and each kind of observation needs protection from different forms of interference. Citizen science projects that compare visible star counts help track how sky brightness changes over time. By asking people to look up and report what they can see, scientists can gather useful information over wide areas. In this way, ordinary observers become part of measuring the changing health of the night sky. The International Space Station can often be seen as a bright, fast-moving point crossing the sky. It does not usually blink like an airplane, and it moves more smoothly than a meteor. For many people, it is one of the easiest human-made objects to spot without any equipment. ISS passes are often best seen a few hours before sunrise or after sunset because the station is still lit by the sun while the ground below is dark. This special lighting geometry makes it stand out clearly against the night. Timing matters, because if both the station and the ground are in darkness, it becomes much harder to see. The ISS usually looks like a steady white light rather than a flashing aircraft. That steady appearance comes from sunlight reflecting off the station as it travels through orbit. To an observer below, it can seem almost star-like, except that it moves quickly across the sky. Astronauts on the ISS experience about 16 sunrises and sunsets in a crew day because the station circles Earth so quickly. The orbit carries them around the planet again and again, each time moving from light into shadow and back. This is a powerful reminder that orbital life follows a very different rhythm from life on the ground. Many satellites are visible because their metal surfaces and solar panels reflect sunlight toward Earth. They are not glowing by their own light in the way stars do. What we see is sunlight bouncing off artificial objects as they pass through orbit. Satellite flares are brief brightenings caused by the geometry between the Sun, the satellite, and the observer. When the reflective surfaces line up in just the right way, the brightness can increase suddenly for a moment. A quiet, moving point can therefore flash more strongly without changing its orbit at all. A satellite moves smoothly across the stars because it is orbiting Earth, not flying through the atmosphere like an airplane. It does not usually show navigation lights or audible engine noise. Its steady motion against the star background is one of the clearest ways to tell what it is. Geostationary satellites appear almost fixed from the ground because they orbit at the same rate Earth rotates. From our viewpoint, they stay in nearly the same part of the sky, instead of crossing from one horizon to the other. Their special orbit makes them behave very differently from lower satellites. Low Earth orbit satellites cross the sky much faster than geostationary satellites because they are much closer to Earth. Their nearness makes their orbital motion appear more rapid against the stars. Distance changes not only brightness, but also the apparent speed of movement across the sky. Satellite trails in photographs can cut across otherwise natural star fields. In long exposures, a passing satellite leaves a bright line that may interfere with the intended image. This has become an increasing challenge for astrophotography as more satellites occupy orbit. Comets can become visible in the night sky when sunlight reflects off their dust and ionized gas. The solid body of the comet is often too small to see directly, but the glowing surrounding material makes it noticeable. What appears in the sky is therefore a larger active display built around a smaller core. A comet's tail points away from the Sun, not necessarily behind the comet along its direction of travel. This surprises many people because it feels natural to imagine a tail trailing directly behind like smoke from a moving car. But the Sun's influence shapes the tail more than the comet's forward motion does. Dust tails and ion tails can point in slightly different directions because sunlight pressure and the solar wind act on them in different ways. Dust is pushed and spread differently from charged gas. That is why some comets show more than one tail and why those tails may not line up perfectly. Comets are often difficult to predict visually because their brightness can change unexpectedly. Their behavior depends on how much material they release, how they heat up, and how that material spreads in space. So even when the path of the comet is known, its appearance can remain uncertain. Some comets are best seen before dawn or after dusk because they remain near the Sun in the sky. Their position may place them low above the horizon in bright twilight rather than high in dark midnight skies. Visibility is therefore not only about brightness, but also about where and when the comet appears. An occultation happens when one object passes in front of another and hides it from view. From Earth, this can produce a sudden disappearance that feels very sharp and dramatic. It is a simple alignment event, but one that can reveal a great deal about motion and position in the sky. The Moon frequently occults stars because it moves noticeably against the background sky from night to night. Unlike the stars, the Moon changes its position rather quickly. As it travels along its orbit, it can pass in front of distant stars and briefly block them from sight. Grazing occultations can make a star blink on and off as mountains and valleys along the Moon's edge alternately hide and reveal it. Instead of one clean disappearance, the star may flicker several times. The irregular edge of the lunar surface becomes visible through the way it interrupts the starlight. A transit is a special case in which a smaller body crosses the face of a larger one, as with Mercury or Venus passing across the Sun. In such an event, the smaller object does not fully hide the larger one. It appears instead as a dark moving spot against a bright background disk. Transits of Venus are extremely rare because they require a very precise alignment of orbital planes and timing. Venus passes between Earth and the Sun more often than transits occur, but usually it is slightly above or below the Sun from our viewpoint. Rare events in astronomy often come down to exact geometry. Mercury and Venus can show crescent phases because we view them from outside their orbits. As they move around the Sun, we see varying portions of their sunlit sides, much as we do with the Moon. This is one of the clearest signs that they are worlds orbiting the Sun in inner paths. Outer planets usually appear nearly full from Earth and do not show dramatic phase changes to the naked eye. Because they orbit beyond us, the viewing angle is different from that of Mercury and Venus. Their illuminated faces remain directed more toward Earth most of the time. Jupiter's 4 largest moons can be seen with ordinary binoculars as tiny points lined up near the planet. Even modest equipment can reveal that Jupiter is not alone, but accompanied by a small family of moving companions. This makes Jupiter one of the most rewarding objects for beginner skywatchers. Those moons were among the first major telescopic discoveries, showing that not everything revolves around Earth. Their motion around Jupiter provided a clear example of another center of orbit in the heavens. This helped weaken older views that placed Earth at the center of all celestial motion. Saturn's rings can become edge-on from Earth during ring plane crossings and then look dramatically thinner. Because the rings are very broad but also very thin, their appearance changes greatly with viewing angle. At certain times, something famous for its wide structure can seem almost to disappear. Saturn's ring plane crossings happen about every 15 years as Earth passes through the plane of the rings. These events are part of a repeating geometric cycle created by the motions of Saturn and Earth. They show how even familiar planetary features can change with timing and viewpoint. Mars has occasional, especially favorable oppositions when it comes relatively close to Earth and appears much brighter. Not all oppositions are equal, because the distance between Earth and Mars varies. At the best ones, Mars can become strikingly prominent compared with its usual appearance. Venus rotates in the opposite direction from most planets in the solar system. This means that if you could stand there and watch the Sun, it would seem to rise and set in the reverse sense compared with most worlds. Venus therefore stands out not just in brightness, but also in the unusual nature of its spin. Jupiter is so large that it dominates the family of bright objects moving through the zodiac. Its size gives it a major presence within the solar system, and its brightness often makes it one of the most obvious planets in the sky. Among the wandering lights, Jupiter often feels especially commanding. The naked-eye planets were known in antiquity because they move against the fixed background of the stars. Unlike ordinary stars, they wander gradually from week to week. This visible motion is what first set them apart and gave them a special place in early skywatching traditions. The sky has different north and south anchor regions because Earth's rotation axis points in opposite directions into space. One end of the axis defines the northern sky's central area, and the other defines the southern one. This creates 2 different polar environments rather than one single global center in the heavens. Southern observers do not have a bright south pole star comparable to Polaris. That means southern navigation and sky orientation often rely more on patterns and nearby guide stars than on one obvious fixed point. The southern sky is no less rich, but it organizes itself differently. Sidereal time tracks Earth's rotation relative to the stars rather than the Sun. This makes it useful for astronomy because it tells you which star positions will be crossing the sky at a given moment. It is a sky-based timekeeping system rather than an everyday solar one. The darkest part of the moonless rural sky is never completely black because of airglow, faint stars, and diffuse galactic and interplanetary light. Even in excellent darkness, nature provides a subtle luminous background. Absolute blackness is not really what a healthy night sky looks like. The horizon often looks brighter than the zenith because you are looking through more atmosphere at low angles. More air means more scattering, haze, and glow. So the same sky naturally appears darker overhead and brighter toward the edge of the world. Atmospheric extinction makes stars near the horizon look dimmer than the same stars higher in the sky. Their light has to pass through a thicker layer of atmosphere before reaching your eyes. This extra air weakens the light, especially when the object is low. Extinction also reddens low stars because blue light is scattered more strongly than red light. As the bluer wavelengths are scattered away, the remaining light looks warmer in color. This is one reason stars near the horizon can seem more orange or red than when they are overhead. Scintillation, or twinkling, is strongest near the horizon because starlight passes through more turbulent air there. The longer path through moving layers of atmosphere causes the light to bend and shift more. That is why stars close to the horizon often sparkle more intensely. Planets usually twinkle less because their apparent disks average out some of the atmospheric distortion. Their light still passes through the same air, but the slightly broader image softens the flickering effect. This is one of the easiest visual clues for telling a bright planet from a star. The color of a bright star can flash and flicker near the horizon because Earth's atmosphere refracts different wavelengths differently. Turbulent air bends the various colors by slightly different amounts. This can produce rapid color changes that make a low star seem to sparkle with tiny reds, blues, and greens. Refraction also lifts objects slightly higher than their true position, especially near the horizon. The atmosphere bends light downward toward the observer, which makes the object seem a bit higher than geometry alone would predict. So the sky we see is subtly shaped by the air through which we view it. The sun and moon can look slightly flattened near the horizon because Earth's atmosphere bends light differently from their lower and upper edges. When these objects are low in the sky, their light passes through a thicker layer of air, and that changes their apparent shape just a little. So the strange flattening is not happening to the objects themselves, but to the path their light takes before it reaches your eyes. Green flashes are rare optical effects that can appear near sunrise or sunset because the atmosphere separates colors by slightly different amounts. Under the right conditions, the upper edge of the sun can briefly show a green tint for a moment. It is a delicate effect, and it depends on a very specific mix of clear air, a low horizon, and favorable atmospheric layering. The night sky often looks darker from high elevations, partly because there is less atmosphere above you to scatter light. With less air overhead, there is less haze, less moisture, and often less glow softening the darkness. This is one reason mountaintops and high plateaus can offer such rewarding views of the sky. Dry climates often provide better stargazing because water vapor can scatter and absorb light. Even when the sky looks mostly clear, moisture in the air can reduce contrast and soften faint details. Dry air helps preserve the sharpness and darkness that many celestial sights need in order to stand out. Cold air can sometimes improve transparency when it is clean and stable, although weather patterns matter more than temperature alone. A cold night is not automatically a perfect night for stargazing, but cold, dry conditions often reduce haze. So temperature can help, as long as the larger atmospheric conditions are also favorable. A dark, moonless winter sky can seem especially sharp because dry air often reduces haze. When the air holds less moisture, stars and bright sky features can appear cleaner and better defined. This gives some winter nights a crispness that feels especially clear and quiet. Coastal locations may sometimes have steady seeing because the ocean moderates temperature changes in the air. When the air changes less abruptly, it can become less turbulent, and that can help telescopic images appear steadier. A coastal sky is not always the darkest, but it can sometimes be wonderfully stable. Mountain observatories are often placed above part of the turbulence and haze that affect lower ground. By rising above some of the thicker and more disturbed air, astronomers can get cleaner and steadier views of the sky. Height, in this case, is not only dramatic, but deeply practical. Dust storms and smoke can brighten the background sky and dim stars even far from cities. Tiny particles in the air scatter light and reduce contrast, making the heavens look washed out. A sky can therefore lose quality not only from clouds or lamps, but also from fine material drifting through the atmosphere. Thin clouds can be difficult to notice at night until they begin to wash out faint stars or create halos around bright objects. Because they may not look dramatic on their own, their effect is often first noticed through what disappears from view. A sky that seems clear at first glance may still be quietly losing transparency. Ice crystals in high clouds can create halos around the moon. These crystals bend and redirect moonlight in ways that produce soft circular patterns. So a simple ring around the moon is often a sign that the upper atmosphere contains countless tiny floating prisms of ice. A 22-degree lunar halo forms when moonlight is refracted through hexagonal ice crystals in the atmosphere. The angle of that ring is set by the way light passes through those crystal shapes. It is one of the most graceful examples of geometry and light quietly revealing themselves in the night sky. The moon can cast distinct shadows on Earth when it is bright enough and the sky is dark enough. Moonlight is far weaker than sunlight, but under the right conditions it is still strong enough to shape the ground with soft, visible darkness. This can make the landscape feel gently defined even in the middle of the night. Full moon light is sunlight reflected by the moon, and it is much weaker than daylight, because the moon reflects only part of the light it receives. The moon is bright to our eyes, but it is not generating that light for itself. It is acting more like a rough, distant mirror, sending a softened version of sunlight back toward Earth. Moonlight makes it harder to see faint stars and the Milky Way, even in dark rural areas. The added brightness raises the background glow of the sky and washes out delicate details. So a beautiful, bright moon can also quietly hide a great deal of the fainter universe. Crescent moons are often especially photogenic because the bright and dark portions create strong contrast. The thin, lit edge stands out beautifully against the dimmer, unlit portion and the dark sky around it. That balance of light and shadow gives crescent moons a particularly elegant appearance. The thin young crescent is usually seen low in evening twilight, shortly after sunset. Because it stays close to the sun in the sky, it does not climb very high before following the sun below the horizon. Its appearance is often brief, delicate, and tied closely to the fading light of dusk. The old crescent is usually seen before sunrise in the eastern sky. This is the late stage of the lunar cycle, when only a narrow part of the moon is still brightly lit from our point of view. It belongs to the quiet hours before dawn rather than the evening sky. Lunar libration lets observers see slightly more than half of the moon's surface over time. Even though the moon keeps nearly the same face turned toward Earth, small changes in angle allow us to peek a bit around the edges. So over many nights, we can see more than just one exact half. Mibration happens because of the moon's orbital shape, its tilt, and the changing viewing angle from Earth. These subtle geometric effects combine to make the moon seem to rock gently back and forth. It is not a true wobble in the everyday sense, but it does allow our view to shift slightly over time. The full moon rises around sunset and sets around sunrise. This happens because at full phase, the moon is opposite the sun in the sky. Its timing makes it the phase that stays visible through most of the night. The first quarter moon is highest around sunset, while the last quarter moon is highest around sunrise. Each phase has its own rhythm and its own typical time of best visibility. Once you learn these patterns, the moon's movement through the sky becomes much easier to understand. Binoculars can reveal star fields, open clusters, and Jupiter's moons far better than the naked eye while still showing a wide stretch of sky. They are simple, portable, and often surprisingly powerful for astronomy. For many skywatchers, binoculars are one of the most rewarding ways to begin exploring the night. A telescope gathers light as well as magnifies, which is why larger apertures can reveal fainter objects. Magnification alone does not explain what a telescope can do. Its ability to collect more light is what makes dim objects brighter and more detailed to the observer. Higher magnification is not always better, because too much magnification can dim the image and exaggerate atmospheric blur. People often assume more power always means a better view, but that is not how telescopes work in practice. A clear, balanced image is usually more useful than an overly enlarged one. Wide-field views are often better for large objects, such as open clusters or long sweeping stretches of the Milky Way. Some celestial sights are simply too broad and spacious to fit comfortably in a narrow, magnified view. A wider frame allows the eye to appreciate how those objects sit within the surrounding sky. Dark adaptation improves night vision, but even a brief look at bright light can undo much of it. The eye needs time to become more sensitive in darkness, and sudden brightness interrupts that adjustment. This is why stargazers are careful about headlights, phones, and flashlights. Full dark adaptation usually takes around half an hour or more for the eyes. The process is gradual, and the sky often seems to reveal more and more stars as your vision adjusts. Patience, in this case, is a real observing tool. Red light is commonly used by observers because it disturbs dark adaptation less than white light. It still allows people to read charts or move around, but it is gentler on night-adjusted vision. That is why red lamps have become so common among skywatchers. A planisphere can show which constellation should be visible for a certain date and time. It works as a simple rotating sky map that matches the season and hour. Even though it is an old-fashioned tool compared with apps, it remains very useful because it teaches the sky's overall geometry clearly. Astronomy software and star apps can help identify objects, but the underlying geometry of the sky remains the same as it is on paper charts. Technology may make the process quicker, but it does not change how the heavens are arranged. The tools become newer, while the sky itself stays orderly and consistent. Long exposure photography can reveal more stars and more color than the human eye can see directly, because the camera gathers light over time. Instead of taking in only a brief moment, the sensor keeps collecting photons for many seconds or even minutes. That is why photographs can show rich detail in scenes that looked much dimmer in person. Smartphone astrophotography works best when the phone is stabilized, because even tiny movements can blur faint stars. The dimness of the sky often requires longer exposure times, and that makes steadiness essential. A simple, stable support can matter more than complicated settings. The histogram in a night sky image helps show whether an exposure is too dark or too bright. Rather than trusting the image only by appearance on a screen, photographers can use that graph to judge how the light values are distributed. It is a quiet, technical guide that helps preserve detail in both sky and foreground. Tracking mounts follow Earth's rotation, allowing longer exposures without turning stars into streaks. As the planet rotates, the stars seem to move across the sky, but a tracking mount compensates for that motion. This lets cameras gather more light while keeping stars looking like points instead of lines. Star trails occur when a camera remains fixed while Earth rotates beneath the sky. During a long exposure, the stars appear to draw arcs as the planet turns. The trails are not caused by stars racing around us, but by our own spinning viewpoint. Circular star trails around Polaris reveal the direction of Earth's rotational axis in the northern sky. Because Polaris lies near the North Celestial Pole, the surrounding stars appear to circle around that point. A long photograph can make Earth's rotation visible in one elegant image. Southern sky star trails circle the South Celestial Pole, even though no bright pole star clearly marks it. The pattern is still there, but it gathers around a less obvious central point. This gives the southern sky its own version of rotational symmetry, quieter, but just as real. Wide-angle lenses are favored for night landscapes because they capture a large portion of the sky and allow somewhat longer fixed exposures before the stars begin to trail noticeably. They are especially useful when combining the heavens with mountains, trees, or horizon features. A broad lens helps tell the story of sky and land together. The Milky Way's structure often becomes visible in photographs before it becomes obvious to the eye. Cameras can build up faint light in ways that human vision cannot match in real time. So an image may reveal dust lanes and brighter galactic knots that were only barely hinted at in person. Airglow can create colored bands in long exposures, even when observers do not notice them clearly with their own eyes. The camera can record those subtle greens, reds, or layered patterns more effectively than human low-light vision. This means some photographs of the night sky are also quietly photographing Earth's atmosphere. Satellites and aircraft can leave unwanted streaks across astrophotographs. During a long exposure, even one passing object can draw a line across an otherwise natural scene. This is one of the small modern challenges of photographing the sky in an increasingly busy world. The color you perceive in the night sky depends both on the object itself and on the limits of human vision in low light. Not everything the sky truly emits is seen by the eye in the same way. Our experience of color at night is partly about the universe and partly about how our eyes work. Under dark conditions, the eye relies more on rod cells, which are good at detecting faint light, but poor at seeing color. This helps us notice dim objects, but it reduces the richness of color we can perceive. So the night sky often feels softer and less colorful to the eye than photographs suggest. This is why many faint nebulas and much of the Milky Way appear mostly gray to the eye, even though photographs show vivid reds, blues, and other colors. The light is really there, but human night vision is not built to display it fully in real time. Cameras and eyes are not seeing the night in the same way. Bright stars can still show color to the naked eye because they stimulate the eye more strongly than faint objects do. A star may appear bluish, golden, orange, or reddish if it is bright enough, and the viewing conditions are good. In that sense, the sky sometimes gives us color not only through instruments, but directly. The number of visible naked-eye stars can change dramatically between a bright city and a dark rural site. The stars themselves do not increase or decrease, but the brightness of the sky background changes enormously. A dark place can make the heavens feel crowded with stars in a way a city rarely allows. Looking slightly to the side of a faint object can make it easier to see, because peripheral vision is more sensitive in low light. The center of your gaze is not always the best place for detecting dim things at night. A small shift in how you look can sometimes bring a faint object into clearer awareness. This technique is called averted vision, and it is especially useful for dim nebulas and galaxies. Instead of staring directly at the object, the observer lets it fall, just off-center in the field of view. It is a simple trick, but a very effective one for finding delicate celestial details. Large diffuse objects can be harder to see than smaller bright ones because their light is spread out over a wider area. Even if the total amount of light is substantial, the object may still seem faint because no one part of it stands out strongly. Brightness per area matters a great deal in night sky observing. Sky brightness, contrast, and transparency often matter more for faint deep-sea eye observing than raw magnification does. A dark, clean sky can reveal objects that no amount of extra magnification could rescue under poor conditions. In astronomy, the quality of the sky itself is often one of the most important instruments of all. Mercury is one of the hardest bright planets to see because it usually stays low in bright twilight near the horizon. Even though it is a real planet and can shine quite well, it rarely climbs high into a dark sky, the way Mars or Jupiter can. This makes Mercury feel a little shy, as if it prefers to stay close to the fading light of sunset or the first glow of dawn. Venus is the brightest planet in the night sky, and that is why people have so often called it the evening star or the morning star. It can shine so strongly that it draws attention even from people who were not planning to observe the sky at all. Its brightness gives it a calm, steady presence that can stand out even when the rest of the sky is still not fully dark. Venus can show phases like the Moon because it orbits closer to the Sun than Earth does. As Venus moves around the Sun, we see different portions of its sunlit side, and that changes its shape in telescopes. So even though it looks like a bright point to the eye, Venus is quietly going through a cycle of changing phases. Mars often looks reddish because its surface and dust contain iron-rich minerals. That rusty color is one of the easiest ways to recognize it among the brighter objects in the sky. A planet's color can tell us something real about the material covering its surface, even from far away. Jupiter is bright enough to be seen with the naked eye, and often outshines every star in the same region of the sky. When it is well placed, it can look strong, calm, and unmistakable. Among the wandering lights of the heavens, Jupiter often seems especially confident and steady. Saturn can also be seen without a telescope, even though its famous rings are too small to resolve with the unaided eye. To the eye alone, it looks like a bright star-like point rather than a tiny world with a ring system. Yet it is quietly remarkable to remember that such a simple point of light is actually a ringed planet. Uranus can be barely visible to the naked eye under very dark skies if you know exactly where to look. It is not an easy target, and many people will never notice it without guidance. Still, the fact that human eyes can sometimes detect such a distant planet at all is a gentle reminder of how capable unaided vision can be. The Moon changes phase because we see different portions of its sunlit half as it orbits Earth. The Moon is always half lit by the Sun, but from our changing angle on Earth, that lit portion appears to grow and shrink. So the lunar cycle is really a slow dance of light, shadow, and changing perspective. The Moon waxes as its illuminated portion grows from new to full. Night after night, more of the bright surface comes into view, and the Moon gradually takes up more of the evening sky. This steady increase is one of the easiest celestial rhythms for people to notice with no equipment at all. The Moon wanes as its illuminated portion shrinks from full back to new. After fullness, the bright area slowly becomes smaller, and the Moon begins giving less light to the night. The cycle then continues, calm and dependable, repeating again and again across the months. The Moon's terminator, the line between lunar day and lunar night, is where shadows are longest and surface detail looks most dramatic. Along that boundary, craters, ridges, and uneven ground stand out more clearly because the sunlight is striking at a low angle. This is why the Moon often looks most textured and detailed when it is not full. Earthshine is sunlight reflected from Earth that faintly lights the dark side of a thin crescent moon. In those moments, the unlit part is not completely black, but softly visible with a dim grey glow. It is a beautiful example of light traveling from the Sun to Earth, then to the Moon, and then back to us again. A supermoon happens when a full moon occurs near perigee, the point where the Moon is closest to Earth in its orbit. Because the Moon's orbit is not a perfect circle, its distance from us changes a little over time. When fullness and closeness happen together, the Moon and look a bit larger and brighter than usual. Because the moon's orbit is elliptical, a full moon near perigee can appear somewhat larger and brighter than one seen when the moon is farther away. The difference is not enormous, but it is real. It is one more reminder that even familiar sky objects are part of moving systems rather than fixed patterns. A blue moon usually means an extra full moon in a season, or, in another common definition, the second full moon in a calendar month. The term sounds as though it should describe color, but it usually describes timing instead. In astronomy, names do not always mean what they first seem to mean. The moon illusion makes the moon seem larger near the horizon, even though its actual size in the sky changes very little over the course of a single night. When the moon is rising or setting, it can feel enormous compared with when it is high overhead. Yet the effect is mostly in perception, not in the moon itself. This moon illusion is tied to the way the brain interprets distance cues near the horizon. Trees, buildings, hills, and the broad landscape around a low moon give the mind more context for judging size and distance. High overhead, those cues are mostly gone, and the same moon can seem smaller even though it is not. Polaris is only our current near-pole star, and has not always held that role. Because Earth's axis slowly changes direction through precession, the identity of the pole star shifts over long spans of time. So even something that feels permanently fixed in the sky is only temporarily holding that place. The Milky Way band contains stars at many different distances, so one glance across it mixes light from many different eras. Some of that light began traveling to us relatively nearby in cosmic terms, while some of it started much farther away. Looking into the Milky Way is not only looking across space, but also across layers of time. Some of the faint haze in the sky is diffuse galactic light, which is starlight scattered by interstellar dust. This means that not all glow comes directly from stars shining toward us. Some of it comes from light being gently redirected by dust between the stars. The natural background of the sky also includes unresolved stars too faint to be seen one by one. Even when the eye cannot separate them into distinct points, their combined light still adds to the sky's softness. The darkness between bright stars is often less empty than it first appears. Even patches of sky that look empty usually contain many stars below naked eye visibility. The eye only catches the brighter members of a much larger hidden population. So an apparently blank region is often full of objects waiting just beyond ordinary vision. The same bright object in the sky can be a star, a planet, a satellite, or even a meteor, depending on how it behaves. A star may twinkle, a planet may shine more steadily, a satellite may drift smoothly, and a meteor may flash quickly and vanish. The sky is full of different things that can look similar at first, but reveal themselves through motion and light. Learning the sky becomes much easier when you begin with a few anchor patterns such as Orion, the Big Dipper, or the Summer Triangle. These familiar shapes give the eye something stable to return to night after night. Once you know a few landmarks, the larger sky begins to feel much less overwhelming. Once a few anchor patterns are known, nearby stars and constellations become easier to identify by a method called star hopping. Instead of trying to memorize everything at once, you move step by step from one familiar feature to the next. In this way, the sky slowly changes from a scattered field of lights into a connected map. The best skywatching equipment is often patience, dark adaptation, and a clear horizon rather than extreme magnification. Many of the finest make-a-day sights need time and darkness more than they need powerful lenses. Sometimes the most useful tool is simply the willingness to stay still and let the sky reveal itself. The human experience of the night sky has changed through history, largely because of artificial lighting, not because the sky itself has become less rich. The stars, galaxy, and many natural glows are still there, but much of them are hidden by modern brightness. In that sense, the sky has not faded nearly as much as our access to it has. A moonless, dark sky reveals more of the galaxy, while a moonlit sky tends to emphasize brighter stars and the landscape below. Each kind of night has its own character. One favors faint cosmic depth, while the other brings a softer balance between sky and earth. Early evening skies in spring, summer, autumn, and winter each favor different groups of stars because Earth changes position in its orbit around the Sun. That orbital motion means nighttime points in different directions through the year. The seasons are therefore not only changes in weather, but changes in which part of space we face after sunset. The brightest planets can often be identified partly because they change position noticeably from week to week compared with the constellations. Stars keep their patterns, but planets wander through them. This slow drifting is one of the oldest clues humans used to distinguish planets from ordinary stars. Constellations help organize the sky, but the real universe is far more three-dimensional than those flat patterns suggest. Stars that seem close together may actually lie at vastly different distances. The familiar shapes are helpful, but they are maps of appearance rather than maps of true depth. Much of what seems like empty black space between stars contains gas, dust, magnetic fields, and radiation that our eyes do not easily reveal. What looks vacant can still be full of structure and activity. The universe is often richer than visible light alone allows us to sense. Some night sky phenomena, such as auroras and noctilucent clouds, belong to Earth's own atmosphere rather than to outer space. They feel celestial because they appear above us at night, but they are closely tied to the layers of air surrounding our planet. Not everything beautiful overhead is far away. Other familiar sights, such as meteors and zodiacal light, come from material within our solar system. Meteors begin as small particles meeting our atmosphere, while zodiacal light comes from sunlight scattered by dust orbiting the Sun. So the night sky contains not only distant stars and galaxies, but also local material much closer to home. Stars, clusters, nebulas, and galaxies represent progressively larger and more distant layers of the visible cosmos. A single star is one kind of object. A cluster gathers many stars. A nebula may be a cloud of gas and dust, and a galaxy contains huge numbers of all of these together. The sky is built in layers of increasing scale. The naked-eye night sky is therefore a combined view of local atmosphere, nearby orbital space, the solar system, our galaxy, and far beyond. One glance upward gathers many levels of reality into a single scene. It is one of the simplest and deepest experiences nature offers. The Milky Way appears as a pale band because we are looking through the flat disk of our own galaxy from inside it. We are not seeing our galaxy from the outside like a picture in a book. We are living within it, and that is why it stretches across the sky like a glowing road rather than appearing as a distant spiral shape. The name Milky Way comes from that faint milky appearance across a dark sky. Long before people understood galaxies scientifically, they described what they saw with simple visual language. The name has endured because the impression itself is still true. The Milky Way is much easier to see from dark locations because artificial light washes out its delicate contrast. Its glow is broad and soft, not sharp and concentrated, so it disappears quickly when the sky background becomes brighter. Darkness is what allows the galaxy's quiet structure to emerge. The brightest part of the Milky Way marks the direction toward the galaxy's crowded central regions. In that direction, stars, dust, and gas become denser and more numerous. What looks like a brighter part of the sky is really a clue about the larger shape of our galactic home. Dark lanes running through the Milky Way are clouds of dust blocking the starlight behind them. They're not gaps where nothing exists, but places where something very real is standing in the way of our view. In this way, darkness itself can reveal hidden matter. When you look at the Milky Way, you are seeing countless stars blended together beyond the eye's ability to separate them one by one. The soft glow is made from enormous numbers of individual suns whose light overlaps in our vision. What appears cloud-like is often simply starlight too crowded to sort out. The Milky Way is so broad in the sky because its real structure spans enormous distances through space. We are not looking at a small local feature, but through a huge galactic system. Its scale in the heavens reflects its true vastness. The Andromeda galaxy can appear from a dark site as a faint, elongated smudge to the naked eye. It does not show obvious spiral arms or dramatic detail without help, but it is still extraordinary that another full galaxy can be glimpsed directly by human vision. A soft blur can hold a vast island of stars. Many of the night sky's most impressive sights, such as the Milky Way, zodiacal light, and bright meteor showers, require no telescope at all. They are broad and natural phenomena, best met with open eyes and a dark horizon. The sky often offers its grandest experiences freely. No two clear nights are exactly the same, because moon phase, atmospheric conditions, season, and the motions of planets and satellites all keep changing the view. Even the most familiar sky is gently rewritten night by night. The repetition is real, but so is the difference. Because the sky repeats its broad seasonal patterns each year, it can feel familiar while still offering new details each time. Certain constellations return, certain planets visit again, and certain rhythms continue. Yet the experience is never perfectly identical. The heavens repeat, but they do not become stale. The quiet appearance of the night sky hides constant motion, including Earth's turning, Earth's orbit, the moon's path, and the drifting of planets. Stillness in the sky is often only an illusion created by distance and slowness. Behind the calm appearance, everything is moving with patient regularity. One of the most remarkable things about the night sky is that ordinary unaided human vision can detect objects ranging from clouds at the edge of the atmosphere to another galaxy, millions of light-years away. Very few everyday experiences place such different scales into a single field of view. And as the sky grows quieter above, it is enough, for now, to let those distant layers rest softly in the dark, one beyond another, while the night remains wide and still.